Oh, I knew we'd forget something. Okay, you only miss the boring bits if you're on Zoom. I can. Yeah, so the only waveforms we had for magnetorotational explosions was ones like this, where they only cover the core bounce phase and they're 50 milliseconds long. So these waveforms are really good for understanding the gravitational wave emission from core bounce, but they're really not good if you want to determine if you can see if your gravitational wave signal was a neutrino-driven explosion or magnetorotational explosion for because these models haven't even exploded yet. So you could have rapid rotation in a neutrino-driven explosion, so we don't even know if they exploded by magnetorotational explosion mechanism. And also, if you're trying to distinguish two models and one of them is 1 second long and the other one's 50 milliseconds long, of course, they're going to be easy to distinguish from each other. So I think our early work on trying to determine the explosion mechanism from the gravitational wave signal, we just mostly proved that we can distinguish long signals from short signals. And we wasn't even sure which ones would blow up by the magnetorotational explosion mechanism. So my next goal was, I need some waveforms with magnetic fields and rotation, because even though we've shown how this method could work, you could never use it for a real gravitational wave detection because the waveforms was not good enough to make an astrophysical statement. So then I did some simulations with Bernard of 39 solar mass star, and one of them, this one that, it's my pointer, that we call B0, has rapid rotation and no magnetic fields. And these two have two different magnetic field strengths. This is the explosion energy here and the time after bounce. And you can see if you add magnetic fields, you get much more energetic explosions. And the models exploded earlier. And this one here that had weaker magnetic fields than that one made a stronger explosion. And also, we see smaller proto-neutron star masses in the models that have magnetic fields. But there's also a caveat here, because in Coconut, we use GR when we have no magnetic fields. And in the version of the code that has magnetic fields, we use Newtonian gravity. So we still, I think in 2D models, they've shown that your gravitational wave amplitude frequency is going to be about 10% higher if you use Newtonian gravity. And I think mine is probably more than 10% higher, but I don't know, is that like still because of that, but it's just the difference is bigger in 3D, or is it actually because of the magnetic fields? So this is still a question I don't have the answer to. So this is what the gravitational wave signal looks like. If you don't know about how to convert these amplitudes into gravitational wave strain, you basically just divide this amplitude by the distance to your source in centimeters, and then you get dimensional strain. So my models that don't have rotational magnetic fields are on average maybe 10 centimeters, and this one's like 100 centimeters. So you have magnetorotational explosions, and you have a significantly higher gravitational wave energy, and you can see them further away. And so now that we had some actual long duration gravitational waves from magnetorotational explosions, first we know that's how they actually explode. And you can see they have this same dominant mode shape, but the frequency is higher, at least compared to my other simulations. So then we tried to determine the explosion mechanism again using these magnetorotational waveforms and a whole bunch of neutrino-driven explosion waveforms. And we used a few different methods. I had a Bayesian method. There was some dictionary learning from the Valencia group. And we wrote a paper. And now we could only determine the explosion mechanism correctly about 70% of the time. But we also included some of Martin and his collaborators' waveforms. But like I said, the neutrino-driven explosions use general relativity, and these ones use Newtonian gravity. So it's also possible that now our model selection study is like showing you the difference between the different gravity instead of actually the difference between the different explosion mechanisms. So we're getting better at this than before, but there's still some ways to go before we can be sure about the explosion mechanism from a real gravitational wave detection. And people keep asking me about jets, so I just put them in so you can see. I'm not an expert in jets, but if you're an expert in jets and you want my data, I'm happy to share it if it's useful to you. So this one that had a slightly weaker magnetic field had much stronger jets, and this one had lots of instabilities in the jets, and it got killed off in that direction. So then I did some 15 solar mass models. My plan when I wrote the proposal for the computing time was that we do some 15 solar mass models to look at the SASE when you have magnetic fields. But then we picked a 15 solar mass model because they usually don't explode, but then everything blew up, and that changed all my plans. This is how it goes sometimes. So they have weak magnetic fields, and we use the SFHO and SFHX equation of state, and 2 of them were rotating and 2 of them were non-rotating. So the rotating models exploded earlier with lots more energy, and I have here the proton-neutron star mass, and so the rotating models have a lower mass, which is not unexpected. And then for the radius, we just have this one model that has a smaller radius than all the other 3, and I wasn't really sure why. But you know the gravitational wave emission is related to the mass and radius, so this also changed the frequency of the gravitational wave emission. So this is what the gravitational wave signal looked like. We found that if there was weak magnetic fields, that the gravitational wave amplitude just came out the same as if there was no magnetic fields. But when you have rotation, even if the rotation's not that strong, the amplitude is always bigger. So yeah, so I find if there's strong magnetic fields, then you get magnetorotational explosions and loads more gravitational wave amplitude. If you have weak magnetic fields, you just have like a neutrino-driven explosion that looks like regular neutrino-driven explosion. So that's what I've seen in these couple of models. And here's my jets again. So these 2 have the same rotation and the same magnetic fields, and this one has jets in both directions, and this one has a super strong jet only in this direction, and I don't even know what happened in that direction. So I don't have any conclusions on why some have jets in both directions and why sometimes they look like this, but it seems pretty random to me so far. I don't have enough models to make a conclusion, I think. So we also looked with these 15 solar mass models at the gravitational wave memory. This was the first time that I bothered to calculate the memory from the neutrino emission, but it's got fashionable now, so we included it. And this is what it looks like in a bunch of different angles for one model. And you can see that these models are quite short, only half a second, but they've already reached amplitudes of 200 centimeters. So I think if I could continue them for 5 seconds, they would reach the same kind of amplitudes that you see in Adam Burrows' papers. And this here is the gravitational wave amplitude spectral density. So you see here, the high frequency modes in the LIGO band, but also down here, you can see that you have this really high amplitude gravitational wave emission, which you probably see in ET because it goes lower frequencies than the others. And this thing here is a gravitational wave detector on the moon. So we're showing signs that if you had a gravitational wave detector on the moon, that supernovae would be a really promising source. But you definitely need more simulations and longer simulations to know exactly how low frequency does this part of the signal go, and exactly how high amplitude does it go, and how often are you going to see it. So. But I've been doing a bunch of 2D models that are much longer to try and measure some of this gravitational wave memory for a longer time. So because I'm a gravitational wave person, I also care a lot about the birth masses of the neutron stars and the black holes. So I did some simulations of pair instability, supernovae, got the models from Alex, and I did some 85 solar mass models and some 100 solar mass models. And I used, again, the SFHO and SFHX equation of state. And the Z100 model undergoes 4 pulsational pulses before, it's about 1,500 years before core collapse. and then it gets stable again. And the 85 solar mass model has a pulse at the same time as core collapse. There's loads of details about these that Alex wrote in the paper because he made the, I just simulated the explosion onwards and he did the pre-explosion stuff. And Alex wrote like figure captions that are like half the size of the paper. So I'm really proud of the size of my giant figure captions. There's loads of details in there. So one thing that we saw was interesting is we get a shock revival before black hole formation. The black hole formation time change depending on the equation of state. So it seems like if you have higher mass models, the difference in the equation of the differences caused by the equation of state are more noticeable. And we just made a quick approximation of what the final, well, like a minimum of what the final black hole masses would be, just based on like the explosion energy and the binding energy. And they're pretty much where you would expect the bump in the black hole mass distribution to be. But Bernard's postdoc Bailey Sykes has a bunch of these models where he simulated the whole fallback. I don't know if you've all met Bailey before, but his work is super interesting and you should definitely check it out. And I also calculated the gravitational wave emission. I don't think you're going to see gravitational waves from parent stability supernovae because they're going to be really far away, but they're good examples of models that have strong SASE. So this one that doesn't explode, you can really see it here, this long part here. And then in the 85 solar mass models is here. And then this is where it explodes and then it starts to die away. So I also have a paper that's submitted and not published where I looked at different kinds of cases where you might get a gravitational wave signal and a neutrino signal, but miss the gravitational wave emission. And so I considered maybe it's just obscured, maybe it just didn't explode and it formed a black hole a long time later, and maybe you get some weak transient that we just missed or something. And then also, I looked at the black hole supernovae, the ones where they undergo shock revival, but then quickly form a black hole. But I only considered the ones where the black hole formation occurs really quickly after shock revival, because if there's like, I don't know, like a second between the two, you're still going to see a full EM supernova, or at least that's what people are writing in their papers. So I went to my parameter estimation model that I made before, which was just this simple bit here. But then I added the second part to it, which can represent SASE. And I just measured the duration of the high frequency mode and the duration of the low frequency mode. So, and you can see that for these different scenarios, they're quite well separated just by looking at these simple properties of how long you reconstruct the gravitational wave signal. And for these non-exploding models, the duration of the SASE mode is actually much longer, but that's just how much I could see at the signal to noise ratio. And you can also tell the difference as well between the slope of this high frequency mode, because in these models that form black holes really quickly, the mass accretion is really high, and the gravitational wave emission reaches high frequencies really, really quickly. It's like a really steep thing. So if you look at these durations and you look at the rate of change of frequency of the high frequency mode, you can pretty much tell without an EM signature which kind of scenario you have. So now my work in progress is I've been doing 150 simulations last year in 2D, and I did 3 different equations of state, non-rotating, slow rotating, rapidly rotating, and 15 different progenitor masses. So I'm still trying to figure out what's going on with all these models, because the most I've ever done in one time before is 5, and it's much easier to look in detail at 5 things than it is 150. So I'm still like, yeah, going through it all. But some interesting things is that we saw some big difference in the different equations of state. So for this one here, the CMF model, only 2 of our masses exploded. And when you use the SFHX or SFHO equations of state, almost all of them exploded except for the 15 and 14 solar mass for this one, and 15 and 18 for that one. So we're going to write a paper about the equation of state effects. And the gravitational waves also vary significantly depending on the different properties. So these ones are pretty short because these are this is the highest mass that formed the black hole the quickest. So like some of them have big low frequency tails, and this one has this giant blob that I'm not even sure what it is yet. And these spikes at the end are black hole formation. So there's all kinds of crazy stuff going on. So I'm going to write a paper about the gravitational wave emission as well. So stay tuned for that. Then I thought, instead of writing a conclusion slide, maybe I can just show you all the things that I did that went horribly wrong that you would never normally see in a paper, because why would I publish that? So you can enjoy my mess ups during the question time.
Questions? Maybe.
Thank you, Jade. That was great. So in the different morphologies of the jets you showed, where the SFHX had a monopolar jet and the SFHO had a bipolar jet structure, which one had a higher explosion energy?
Don't think I put it in. Oh, I did look just before. So in this case, this one had the highest explosion energy.
Which is what I'd expect, because
yeah,
we've seen this too. There are trends with the dipolar structure, not the bipolar, but the dipolar structure of the ejecta, even without a B field. And when you showed it earlier that there was a model with a 10 to the 10 Gauss and one with a 10 to the 12 Gauss, the 10 to the 12 Gauss had a monopolar jet, one had one direction, and the other one had a bipolar jet. And so I'm wondering if it's because not directly related to the larger B field, but to the larger reservoir of energy in the B field. And so you can explode it earlier and you have infall funneled in on the other direction that leaves behind this geometry.
Yeah, so I'm definitely not an expert in jets and what's going on there. So I think more investigation's needed.
Okay, maybe just quick question.
Hey, Jade, beautiful work, presentation. Thank you. Just a quick question. We know that the turbulence in the post-shock region can ramp up magnetic field strengths. It does ramp them up. But obviously, when you have no rotation, you didn't. How large did the magnetic fields get? Just out of curiosity, do you know?
Oh, I'd have to go and look it up. So I don't remember off the top.
I would be interested to know that, because you've got a real situation, you've got a real time scale, so it would give us an idea of how much we can expect, modulo numerical issues of resolution, things like that. But anyway, we can talk offline.
Yeah, okay.
Okay, so let's thank the speaker again.